Welcome to this video. In this video, let us derive work required in a multi-stage compressor with negligible clearance volume and without an intercooler. Now, multi-stage compressor, we have seen that a compression is done in more than one stages. So, in that case, we can have one lower pressure cylinder. If let us say we are compressing from 1 to 8 bar, we are going for 1 to 4 bar in the first cylinder and then 4 to 8 bar in the second cylinder. So, delivery of first cylinder is connected to the next cylinder, alright. Now, this is our first cylinder and this is our second cylinder. So, in this case we have considered two-stage compression and it can be extended also. Now, we already know with negligible clearance volume or without clearance volume, we have already derived work equation, alright. So, let us start from the diagram in a pressure versus volume. Okay. Now, first stage is we know, we will start from here, the suction. And then there will be a compression, polytropic compression, and then this delivery, now this is our compression in the first cylinder or first compressor, then it is further compressed in a second cylinder, alright. Since the delivery is connected to the next cylinder, this will be further compressed with same polytropic compression, let us say 3, okay. Then it is delivered, okay, then it is delivered, this will be our 4. Now, however, we will keep this line just to know the pressure. So, this will be our 5. Now, this is again PV power n is equal to constant, PV power n is equal to constant, okay. Let us put the arrow mark, and this is pressure is equal to constant, and this is again pressure is equal to constant section. Now, we know that for first stage, so the total work required will be work required in the first stage plus work required in the second stage, okay. Now, what is the work required in the first stage? Without clearance volume, we have already derived n by n minus 1 P1 V1, okay, into the pressure ratio, because here there are two pressure ratio, I will consider this pressure ratio first, okay, because that is what is in the first stage. So, for the first pressure ratio, that will be, let us say, P2 by P1 whole power n minus 1 by n minus 1. So, this is our first stage, alright. For the second stage, we can write the same or we can reduce the same work equation. So, n by n minus 1. Now, initial pressure for this will be P2 V2, then we can have the pressure ratio here will be P3 by P2. So, for the second stage, the pressure ratio will be P3 by P2 whole power n minus 1 by n minus 1. So, this will be our equation for two stage. Now, imagine if this is isothermal compression, this we can take it out common, but however, this can be further simplified, we can take n by n minus 1 common, n by n minus 1 common, P1 V1 P2 by P1 whole power n minus 1 by n and similarly we can write P2 V2 P3 by P2 whole power n minus 1 by n, and this minus 1 we can write it like minus 2. So this is for two-stage compression. Now we can write it in general for n stage, let us say, for let us say for n stages, where n is number of stages. Okay. Now this is for two stages. Alright, whatever we have derived is for two stages. Now for n stages we can write n by n minus 1. Now P1 V1, similarly this will go up to, this equation will go up to, let us say, and plus so on. This will be same stage, like P2 V2 is for two stage, so this will stop at a place where n stage, and P3 is plus 1 we can write, so Pn plus 1 divided by Pn, so that is the number of stage, and this will be minus number of stages. So this is a general expression where you can replace this by number of stages. Okay. Now let us consider work required in multi-stage compressor without clearance volume but with an intercooler. Now what is an intercooler? Now intercooler is a device where we can bring down the temperature. Okay. Now very important, let us start from the same PV diagram. Okay. Now this was our suction, then compression in the first stage. Now in the last case, this was directly fed into the second cylinder. Now let us cool it before we go for compression. Now why do we cool this? Now it is very important that we are trying to compress a fluid, alright, we are trying to compress a gas. Now in the process, if the pressure is high, in the process of compression, pressure becomes higher, and as the pressure increases, temperature also increases. Now this is what we do not desire in compressor, because temperature rise will push the piston backwards. I mean, the side effect of this temperature rise is volume will also increase, but on the other side we are trying to compress, but increase in temperature pushes the piston in the opposite direction, which increases the more, consumption of work. Okay. So because of which, if we can cool it by circulating water, so we can bring down the temperature. So before sending this higher temperature air to the next cylinder, let us cool it by circulating water around this air, compressed air. So this will be point, let us say 2 dash. Now we have, this process 2 to 2 dash is intercooling. Now very important, how do we want this intercooling to occur? I mean, let us say the initial temperature is T1, intercooling, I mean, we should bring this 2 back to T2 dash. I mean to say, if this is at room temperature 30 degrees Celsius, let us say after compression it becomes 100 degrees Celsius. Now how much temperature we can bring this down? If intercooler is good, if intercooler is perfect, we are circulating water around that intercooler by 30 degrees Celsius water. So it should bring back this temperature to same 30 degrees Celsius. So if intercooler is perfect, so I can join this, in order to just to show by an isothermal line. What is an isothermal line doing here? We just want to show that T1 is equal to T dash. So this is a temperature constant line, we can say. That has nothing to do with this process actually. I mean 1 to 2 dash is not a line. It is just a temperature constant which is just showing that T1 is equal to T2 dash if intercooler is perfect. Alright. So So that is what intercooling, T1 must be equal to T2 dash. Intercooling brings down the amount of work which is required for compression because temperature is brought down. Now let us go back and go to the next stage. So from 2 dash it is further compressed as we were discussing, that is according to the law PV power N is equal to constant. Then we will deliver it, then again we will come back to this point. Now whatever this line which we are drawing, this is just to show that this is a constant pressure line. Alright, now this is our point 3, point 4, and let us say this is our point 5. Now work required is again the same equation. Work required in this will be equal to work required in the first stage plus work required in the second stage. Now that can be rewritten as N by N minus 1 P1 V1 into pressure ratio of the first stage, that is P2 by P1 whole power N minus 1 by N minus 1 plus second stage N by N minus 1. So P2 V2, do not worry about this, okay, if you want P2 dash V2 dash into P3 by P2, the pressure ratio there in the second stage N minus 1 by N minus 1. Now since we are talking about intercooler perfect, so we can write P1 V1 is equal to P2 dash V2 dash. Okay, because intercooler is perfect, that is what is the assumption. So for a constant temperature we also know that PV is equal to constant. So P1 V1 must be equal to P2 dash V2 dash. So therefore, so work required will be equal to, now I can take this also common now, N by N minus 1. So P1 V1 I will take it common because that is going to be the same. And we can write this P2 by P1 is the first stage, N minus 1 by N minus 1. So similarly here second stage, and this will be minus 2. So this is for 2 stage. So for 2 stage. Now let us generalize this expression for, let us say for n number of stages, n stages. Okay, then the same equation can be written as W number of stages will be equal to N by N minus 1, and this is initial pressure P1 V1, initial pressure and volume, and this will go up to P2 by P1, let us say first stage, and then second stage, and so on till Pn plus 1 divided by Pn minus number of stages, it will go up to, if it is 3 stages it will be 3. So for n number of stages this will be n. Okay. So this is the general expression for work required for multi-stage compressor without intercooler. Let us see you in the next video. Thank you.